At some point, I went to my friend and co-founder Raphael and said, well, at the end of our PhDs, when we have nothing to lose, we can give it a shot. And 5 years later, here we are, 150 people at Alice and Bob. And the technology is definitely delivering on its promise. You failed miserably, you can tell your children, we had this amazing angle. It failed for a completely unfair reason. But then you're proud to have given it a shot. The goal of quantum computing, we need to escape the noise arising from our classical world. And that resembled a lot Sputnik, which was the first man-made object to escape gravity and reach a stable orbit. Once you got Sputnik, then you have a platform. I'm an extremely firm believer in European tech, but it's gonna take a lot of audacity. Audacity in almost a military sense. It's about establishing that bridgehead and hoping that the cavalry will join.
Welcome to another episode of the Quantum Economy Podcast. Today I'm joined by Théau Peronnin, the co-founder and CEO of Alice and Bob, one of Europe's most exciting quantum hardware startups. He is a physicist by training and passion. His groundbreaking work on bit protected qubit designs led to the development of the cat qubit and ultimately to founding Alice and Bob. In our conversation today, we'll look at why embedding the error correction directly into the qubit might be a game changer, and we'll look at Europe's role in the global race for quantum. And we also take a look at the challenges of commercialization. We take a deeper dive into the cultural dimensions of emerging technologies and why quantum is more than just computing power. And we'll look at why the idea of a technological singularity might shape our future. Here is the Quantum Economy Podcast with Théau Peronnin.
Yeah, Théau, first of all, it looks like you're in a rainy, gray Paris today. Good to see you and good to have you here. Thank you for joining me.
Thanks, Anders, for having me. And yeah, indeed, it seems a bit foggy with my camera at the moment, but I'm sure the weather on the quantum ecosystem is definitely sunny at the moment, and I'm sure we'll have a lot to discuss.
That's what you do when you focus on the hardware part, right?
Exactly.
And not on the front-end application layer. No, that's good. But for people that don't know you, could you just give you a short, brief insight to what I found fascinating, how you came from your academia career and now building this European quantum startup that has really gotten traction. Just because, this is the fast track record that you have managed to build. And we just was curious, some quick learnings and where you come from and how you've gone about with your co-founders.
Yeah, so I'm a physicist by training and passion, studied at École Polytechnique. Specialized in quantum physics at the École Normale Supérieure, so typical French education at that point. And then I went on with a PhD in experimental quantum physics on the kind of technology we're using today, so I'd say advanced superconducting qubits. And very, very early on during my PhD, two things were obvious to me and highly frustrating. The first one was that around my co-founder Raphael and myself, there was this amazing lineup of physicists, Benjamin Huard, Zaki Lertas, Mazia Mirami, and so on and so forth. And they were completely underfunded, and yet they managed to remain very relevant in the type of science that we're doing. And it felt absurd seeing them spend half their day looking for pennies to finance their research. At the same time, in the late 2010s, you had many startups getting launched across the Atlantic, not necessarily with lineup that impressive. So that was the first thing that frustrated me, especially coming from a personal background, familial background that is not accustomed to the use of academia, coming more from a corporate family. And the second aspect was the technology. This group of researchers from CNRS, CEA, INRIA, and other labs in France were on the verge of designing a rather novel and extremely promising approach to quantum computing, which is how can we redesign the building block, the qubit itself, to directly build in some level of error correction by design within the qubit. And that gave birth to the cat qubit. And when my co-founder and a bit of myself, mostly Raf and his PhD advisor, Zaki Lertas, managed to make it work and deliver its promises of correcting one of the two types of errors by design, it all reached a point where it was absurd not to give it a shot. So at some point, I went to my friend and co-founder Raphael and said, well, at the end of our PhDs, we have nothing to lose. We can give it a shot, dedicate a couple of years to see how far we can take this technology and project all together. And he signed up for it. And 5 years later, here we are. We're now something like 150 people at Alice and Bob. And the technology is definitely delivering on its promise. So I guess that was a right gamble to do. And I think at the end of the day, I'm really glad we did, because the way I convinced him was really to say, well, imagine us in 10, 15 years, 20 years, I don't know, telling our children, well, we were part of that quantum wave. We had an idea, but it was not meant for us. You feel a bit of shame. Whereas if you give it a shot, you fail miserably, you can tell your children, we had this amazing angle. It failed for a completely unfair reason. But then you're proud to have given it a shot. And so far it's working well. So we're even prouder. And this is how we started Alice and Bob.
That's amazing. It's fascinating. There are so many things that I would like to ponder on that. I mean, obviously, introducing Alice and Bob and the cat, you got to go around talking about your company and what the cat has to do with it for everyone outside of the quantum realm. So I found that fascinating. But speaking of that, underfunded scientific substance and do you think that is a trend that is now driving the industry? So, one is obviously 100 years ago, we had the theoretical foundation of quantum theory, quantum physics, and now we have the practical implications. And do you think that this is something that we are seeing now, a shift that is moving a lot of these great, brilliant minds out of the academia and into the corporate world? So do you think that the breakthroughs now will come much more out of like companies like yourself, because you have some funding, you have the bright minds, and they work on these breakthrough technologies? So is that a trend that you will see, that a lot more will now be moved into the corporate world when it comes to breakthroughs in science?
I don't know. I guess I'd love to nuance a bit what you just said in the direction of saying, well, what we're seeing today in 2025 is really a broader spectrum of places where you can do research. When you think about it, quantum startup, especially on hardware, were nothing more than special purpose research lab on steroid with short timelines. And people often do the comparison with Los Alamos during Second World War, but I think you can also think of NASA. NASA was kind of a corporate company, a governmental company driven by one mission to build a machine to get us create that platform. It's just that at the era of new space, the way societies think about those kind of grand technological projects is to lean more heavily on the private sector, more explicitly on the private sector. But it's still, it still has, it's still highly driven by public funding. Whether it's in France, in Europe, even in the US. When you think about the DARPA Quantum Benchmark Initiative, it's the tip of the iceberg of how much of the private sector is driven by public funding and public procurement. So I think it just, the line is blurring a bit between academia and corporate. I think we're also seeing this in AI. When you think about the type of research that is happening at the moment on foundational model, those kind of thing, on scaling large model, just to say that when when you're reaching that level of intensity of research, where that level of excellence that is way beyond just the scientific one, it's how you organize researchers to work efficiently together. You need special vessels, and those are the startups at the moment. Maybe tomorrow it will be a different type, but I think the essence of the grand project is the same throughout the 20th century as it is today.
Yeah, so you still see room for some academia Nobel lectorates coming out, not only the shift towards all Nobel Prizes being rewarded to the big corporate labs in the future.
I really hope so. I mean, in the DNA of Alice and Bob, academia is one of the core values. We know where our roots are, and Raphael and myself, we were born and raised physicists, and that leaves a mark, I guess. And it's also in the kind of culture you're building. I mean, it's hard to find a demographic that is that free thinking as physicists. They value their individual freedom a lot, and when you join a group, by necessity you're giving up a bit of your individual freedom to the group, whether it's a company or whatever type of ensemble of humans, and that trade-off has to be thought in the context of the project you're doing. So when you have a clear mission statement, like building a large-scale fault-tolerant quantum computer, it's easy to see if it's fair, and I think this makes sense today. Now, in the way we're organized at Alice and Bob, we're still extremely symbiotic with academia. We share PhD students. We have almost 10% of the team that is in a format that we called in France thèse chiffre, so PhD that is half industry, half academia. We also have a scientific board plus a consultative board to challenge us, to feed us with ideas, and we're splitting projects between those that are core to our roadmap that we do internally and those that are more exploratory ideas, more breakthroughs ideas, but too risky to be part of our core roadmap at Alice and Bob, that we share with our academic partners, and they go on and do work their magic there. And in exchange, we feed them with a lot of tools, software, mechanical pieces. I mean, it's about a win-win situation where we're going like bulldozers through the main avenue, and there are scouts exploring novel paradigm. And there is a lot to invent still. I think we're just scratching the surface of quantum hardware and quantum engineering. So many things to discover yet.
Yeah, no, I agree. But I think the NASA reference, I like that. I think I've heard you reference the Sputnik moment of quantum computing, right? So basically, the foreshadowing the NASA journey. What would be the equivalent in the quantum space and quantum computing, in terms of the Sputnik moment, then to lead into that NASA growth path focus, the specialized computing?
Yeah, I think there is a very strong parallel in the sense that the goal of quantum computing, for quantum computing to work, we need to escape decoherence. We need to escape the noise arising from our classical world. And that resembled a lot Sputnik, which was the first man-made object to somehow, in some sense, escape gravity and reach a stable orbit. It's unclear whether the Sputnik moment of quantum computing has been met already. Do we have already a true logical qubit that can remain coherent for arbitrarily long time? I'd argue it's not yet fully there, but we're inching towards it for sure. And from there, once you got Sputnik, then you have a platform. You can send stuff in space, and it's quite the same in quantum. Once you have the first handful of, or rather 100 logical qubits with sufficiently low remaining error rates, then you can start doing useful stuff. And that is something that the community has clarified very well in the last 2 to 3 years, to say what is really the threshold of impact of quantum computing. And I think now it's crystal clear. It's around 100 logical qubit with a rate between 10 to the minus 6 to 10 to the minus 8. And so now it's about building the machine to get us there.
Yeah. I mean, I agree on that, and I think if I would be interested in your take on it, because I know you would obviously have a lot to say about how you receive with Alice and Bob and your cat qubits and why that is better. But what is your take on the various superconducting circuits and also like the spin qubits and the various approach to trap ions, like the whole essence of where do you see promising breakthroughs like this year even or going into 2026? Are there players that you think are like ahead of the game, or where you see very promising states of the development, approaches that you think are really promising to drive that transition into that commercial path?
I think there is so many brilliant minds across the board in so many different platforms. That's what makes this race, or filter as Jeremy O'Brien says, so fascinating. And it kind of echoes the first computing revolution in the first half of the 20th century, where you had electromechanical relays, vacuum tubes, so many different modalities for classical computers. Now you have that much diversity in quantum, with a lot of promising aspects on every front. Obviously, I'm deeply convinced it's going to be superconducting qubits and cats, but each platform has really pros and cons. Another aspect I find remarkable is how every hardware vendor's roadmap converge around the same timeline, which is 2030 plus or minus 2 years to get to a few hundred logical qubits. So it's really firming up the whole roadmap, and it echoes those public procurement programs. I think that the next 5 years are going to be fascinating in seeing how all those modalities progress. But the way I encourage people to think about it is to say, well, let's assume everyone succeed in their own R&D. I mean, who am I to judge how hard it's going to be to control more atoms or have fewer losses in fiber optics? I don't know. That's not my specialty. But let's just say everyone succeeds on their hardware challenges, and let's have a look at what the end game look like. And this is how I compare a platform, saying, well, atomic systems are slow, and that seems to be quite fundamental in some sense. How slow they are, one would argue they recoup some of that slowness through transversal gates, but that's technicality. Photonic platform seems expensive. Superconducting seems to require cryogenics, and some people are skeptical about how scalable that is. It's going to be fun for sure.
How do you look at nitrogen vacancy, the NV centers, and that approach, and also maybe your thoughts on? Do you think we need to make the approaches in future to fit on a chip and have that chip production of the quantum chips, or what is your take on how this will evolve in that space? I know these are two different questions, but I mean some of these NV structures are also related to chip production, right?
Yeah, I'm not an expert of NV centers. My understanding is that there is a bit of misconception on the fact that you can operate them at room temperature. If you want state-of-the-art performances, many of the parts needs to be cryogenics at cold temperature. And then, I mean, what I've seen in every modality is how brutal the threshold of error correction is. Because at the end of the day, we have an absolute scale of performance, which is given by the level of individual qubit performances you need to meet to trigger error correction. And from there, sky is the limit. I mean, as soon as you're sufficiently below threshold, 10x below threshold of error correction, then you can do whatever you want. But what we've seen, at least in superconducting qubit with transmon, is how tough it can be to break free of some glass ceiling in terms of performances of the physical qubits. So when when you see promising emerging platform, it's very exciting because you're tempted to say, well, it's gonna follow a performance sort of Moore's law that doubles its fidelity or whatever. But it might also just fall short of the requirement of fault tolerance. And so for now, it's too soon to tell, for example, for NV centers, but it's also true for spin qubits in some sense, where distant gates, gates between distant qubits is, in my understanding, not yet crystal clear in terms of performances, things like that. So I'm all for surprises in that regard, but it's far from done for sure. And the second half of your question was, sorry, I lost the...
Yeah, no, it was basically the chip part. If you think, we had to have, build these structures out of some of the current hardware approaches and put the quantum chips into production.
Yeah, I think, in my opinion, this is really not the challenging part. Every part of this endeavor is challenging, so it's but it's not the worst one. The manufacturing, at least superconducting qubits, is rather simple in terms of processes, but it has to be done very cleanly, and that is the tricky part. Now, the challenge, as with any semiconductor, is going to be yield at scale, and how much dead qubits can we tolerate in a given architecture, things like that. And I think there is a lot of work around where the way we think about it at Alice and Bob is really to say, okay, what can we do about that? What we can do is reduce the number of qubits required, so that the scale we need to achieve is much more reasonable. For example, to get to 100 logical qubit, we only require about 2,000 cats, which would definitely fit within a standard fridge, and a large one, but not some sci-fi tech for sure, and on a single wafer without too much complexity added. So there is room to reduce that. Then you're not limited in the size of the chip you can do, or ensemble of chiplets, which is not true for classical semiconductors, because you need to you have some competition between your clock speed and the size of your processor, which is not true in quantum. Now, the real challenge, in my opinion, and this is true across modalities, is what is controlling the qubit. That is the part that is going to be really hard to scale. It's the control electronics. And this is where, for example, atomic systems have an edge in how much control electronics per qubit they require. Because, when you go from one modality to the other, the prefactor of how many FPGA boards or classical control electronics per qubit do you need might change, but overall it still scales linearly with the number of qubits, which, when you run the numbers, is what is going to dominate the cost of your machine. It's not the quantum part, it's the classical part of the setup. And so that is going to be challenging. There's a lot of options to solve that. You can think of cryo-controlled electronics. You have rapid single flux quantum, superconducting classical electronics. You can also build ASIC. You can do a lot of fancy stuff to solve that, but it's not done yet. A lot of work to be done there.
But you touched upon the limits of conventional, GPUs and CPUs, and how confident are you that there will not be significant breakthroughs in that field? I've seen some recent publications on some kind of negative capacitance field effective transistors, like the NC-FET that was communicated just a couple of days ago, and how that basically has an almost quantum-like effect on the efficiency when it comes to speed and processing and usage of energy. Where do you see the boundaries here? The question goes direction of how much how far do you need to go in with standard CMOS materials when they keep making these improvements, and you can put in compute on it and you can become more efficient on the energy. Is that something that you see as a risk?
No, absolutely not. The question you're asking is actually a Nobel Prize question, which is are we sure the complexity, the class of problems addressable with quantum computers will not be met by classical computers? And that's where the answer is we absolutely do not know. What we know is that there is at least one problem, factoring large number, where many very smart people have thought about it for very long on classical computers and classical means and did not find a way to solve it. And there seems to be a way with quantum computers. So the class of problems addressable with quantum computers seems to be larger than that of classical. Now, the boundary you're mentioning does not put at risk the fundamentals of quantum computer, in the sense that if you accept that the problems with super polynomial speedup or exponential speedup, to say simply, won't be matched by classical computers. Now the competition remains on polynomial speedup, like Grover algorithm to search a database. And the truth is that when you're serious about quantum, you're not really looking at those polynomial speedup use cases, because it's going to be so tough outperforming classical computers. The size of the problems you need to consider is so huge, and classical computers are so fast. But as long as you have super polynomial speedup, good luck catching up with that. And then I'd say maybe to broaden a bit, the question is to say, is quantum a threat for GPUs and CPUs, to invert the question? And the answer is yes, but not for the reason you might think, because we're not gonna replace CPUs and GPUs. That's for sure. Future of computing is a hybrid mix, just like GPUs did not replace CPUs, but the value, the margins moved from one to the other. The question is the question of marginal utility for the user. Imagine you have a large computing center with 10,000 GPUs and 100 logical qubits. If you double the number of GPUs, you gain linearly in terms of computing power with actually diminishing returns. If you double the number of logical qubits, all of a sudden you have problems that were untractable that becomes tractable. So the marginal utility for the user is strongly in favor of the quantum part, which means that the margins, and so the money, the investment, the control, everything follows the margins, will be on the quantum side. And this is why, in my opinion, players like NVIDIA are starting to move more aggressively into quantum, not because GPUs are going to be obsolete, they won't, but because they might lose their edge in margins.
Yeah, that was the famous beginning of 2025 moment where Jensen Huang came out and said, 20 years away, and the next day he launched the quantum day. So maybe that was just to get in on the race at the cheaper evaluation. But so you have, you say you come family-wise, the corporate background. So I think, is it true that one of these misconceptions that you have in the industry when you talk to clients is basically saying that it's not about updating classical algorithms and speeding them up, but it's enhancing and enabling to ask new questions or build new algorithms that today are not accessible?
Yeah.
Is that a fair statement?
Yeah, and I think it's very hard for large corporates to address that properly, because it's both extremely technical, very industry specific, and an existential threat. So it has to be dealt at the COMEX level. For example, we worked with a large French utility company, and so material science, chemistry. They have challenges all over the board. And the thing is, the whole org and the process and the playing field itself in everyone's mind is limited by sort of the classical way to approach the problem. This is what we can do in R&D. Those things are just sci-fi. Stop dreaming. Let us optimize existing processes. The way we optimize them is through rigorous empirical research. And when you think of what quantum will unlock tomorrow in terms of chemical engineering, proper design, as a physicist, I often tease my chemist friends saying, well, the purpose of a quantum computer is to make chemistry an exact science. What I mean by that is really a playground for engineers, saying, well, what do you want to achieve? How do you design your molecule, its catalyst, whatever? it's going to be completely different. And so what we're gonna, in my opinion, see is a burgeoning ecosystem of startups that take a completely new look at century-old problems. Yeah. I mean, quantum has been obsessed with FEMOCO for fertilizer synthesis, but that's just one in so many catalytic processes we have throughout industry. And the challenge for incumbents is going to be to how do you nurture internally this kind of breakthrough innovation in companies that have 100,000 employees. I mean, it's very large corporates, and how do you navigate those emerging startups in this? It's definitely the same kind of war CEO mindset you're going to need in large corporates, as we're seeing now happening in some AI breakthroughs with definitely the FANG or companies that are moving so aggressively in the field, because at the end of the day, those are existential threats to their historical businesses. So yeah, it's going to be very exciting in many ways, and there is a lot of first mover advantage at play, because when we're talking about molecules and chemistry or materials, the IP will matter a lot, because those are things that will last. And the one who can secure cheap, efficient batteries or room temperature superconductors, should they exist, those are extremely valuable patents you might grab. And so, yeah, the first mover advantage, it's hard to think about properly for large corporates.
Yeah, no, that's very interesting, because it's very much aligned with what I call anticipatory leadership. So basically saying that we look at progress, exponential progress over a path of 80 years. So it makes a lot more sense to bet on breakthroughs in science and technology than it does to look at studies of the past. Yeah. So you mentioned chemistry. I would argue the same with biology. Yeah. We will hack biology. And what does that mean? We don't know exactly what it means, but if we could foresee abundance of energy, where the marginal cost of energy plunged towards zero, and you have extended the periodic table from today 119 elements to 130 or 140 even, that type of thinking to say, what are the use cases where we can apply abundance of intelligence and compute power and energy to some scenarios, to think, in a different way about use cases and businesses. And this is, I think, one of the lacking skill in business. But how do you go about then to commercialize? Because, obviously, you look at what you said in the beginning with a roadmap that seems pretty coherent and pretty stable across the various approaches. But still, this is also an industry that needs to be fueled by, output and actual business use cases. How can, companies such as yourself, beyond the hardware part, look into use cases where you can clearly make a prediction that this technological breakthrough or scientific breakthrough will happen, and there is a high likelihood that humanity will move towards a such and such scenario and do this, meaning you will generate some new billion or trillion dollar industries. How can you take on that challenge, and what are some industries that you think are promising to look at right now for sales purpose and for commercialization?
Yeah, the way we think about it at Alice and Bob is really trying to put things in the right order. So when you look at what we know about quantum algorithms and applications, it's a spectrum. Some will require tens of thousands of logical qubits, and other could be useful very early on. Now, when you look at those that are going to be useful or impactful, should I say, very early on, those are typically deep physics, material science, early chemistry. That was the reason why I focused on chemistry earlier. And then you can ask yourself, well, is there already a market for that type of computing? And the answer is yes, there is. It's called the HPC market, high performance computer market. It's often large, some people say data centers, large computers that are state-owned or with finance through some level of government support. And those are our first clients. They're the one we go after with our early prototypes of quantum computers, because for them it's great. Building platform, we're selling some of the very first fault-tolerant machines or platforms on which you can play with fault tolerance and error correction, so that they can build their stack on top of that, their software stack. And when you look at their workload today, there's a major chunk of it that is chemistry, DFTs, those kind of things. So it's pretty natural for quantum to address that market first. Plus, it creates a smooth transition from being a field supported by government engagement, just like SpaceX was in its time because of dual use and sovereignty concerns and things like that, and to reaching an early market from today to 2032 before addressing broader use cases. And broader use cases for us, our typical positioning is that of an NVIDIA-like. We want to sell hardware to large computing infrastructure, whether it's hyperscalers, large mainframes of corporates, whoever you like, but that is a much broader and wider market than just the HPC market. So it's a spectrum. You have to look at the applications and their requirement really directly in their eyes and saying, well, this is, for example, optimization workloads, they seem to, at least those with proper quantified speedup, seems to require a bit too much qubit to be the first ones. The first one are really going to be about material science and what I call deep physics, which is things like spin chains or, historical problems of physics.
No, that's fascinating. How you reflect on that, but then maybe you touch a little bit upon on this topic, but maybe it can be some more specific on how you see it with Alice and Bob, because I think one of the things that you state is that you are able to reduce the qubit count for fault-tolerant qubits because of your approach by an order of magnitude, whatever. And what are like the numbers that you would look at then to say that this is some kind of, quantum supremacy would be played with the far-stretch, but in a near term, what are like milestones of qubits where you have your view on fault-tolerant qubits as comparison to the million or whatever the baseline is for other, competitors in the market?
Yeah, indeed, the whole point of our approach is to design fault tolerance directly within the qubit to reduce the level of redundancy required in the whole architecture. And when you connect that with what I mentioned about the cost of the overall machine being directly linked to the classical control electronics, what I mean is that the machine we're building are not just going to be much simpler, they're going to be way more cost effective. And that also makes our whole R&D much more affordable. This is how we manage to compete with players that are much larger than us so far. And so the roadmap, for us is pretty straightforward. It's about first, on the helium chip we're working on at the moment, publish our first prototype of logical qubit experiment where we demonstrate how below threshold we are, but because it's only going to be a small scale chip, we won't be able to push the distance of the code that far. Then by the end of 2026, we'll be targeting lithium, a 48 cat qubit device, which will be sort of the MVP, the minimum viable product of a fault-tolerant quantum computer that you can operate either as one very good logical qubit, demonstrating that proper Sputnik moment, how we escape decoherence, things like that, or as a handful of logical-ish qubit, where you can do almost every quantum operation you expect. Then you need beryllium to add the magic state factory, the one tough quantum gate to combine with quantum error correction, which is often a bit overlooked. And during the summer, we just published a new architecture, very promising, very efficient at that. And then the target for us is for 2030 to reach the chip we call graphene with 2,000 cats, and delivering at least 100 logical qubits with a rate below 10 to the minus 6. So really a machine that can start to do things that are completely untractable for classical computers, and that is not tautological. I mean, it's not using a quantum computer to simulate itself. And so that's, I'd say, the broader view. Maybe to be a bit more specific about the numbers, the way we often benchmark our architecture is against Shor algorithm to break RSA 2048. Not that we're bad guys or we love to break the internet or Bitcoin. It's a petit curve, but it's same. The reason it's that it's an unambiguous problem, math problem. So it's clean. We know what we're talking about. It's really Plus it has historical value. And the standard architecture a la Google historically was benchmarked at requiring about 20 million. There has been recent progress on the algorithmic side that brought that down to a million, but we haven't yet transpired that to our architecture. So we're still running the number. So I'd stick to the 20 million for now. And so when you look at cat qubit approach with exactly the same hardware assumption in terms of quality of manufacturing, thing like that, we reduce that number to barely 100,000. So 200 times fewer qubits. So now we're working on the numbers to see with this new version of Shor algorithm how low we can get that. But it's definitely something that's going to happen in the early 2030s in our roadmap. So I wouldn't hold my Bitcoin for too long if they forgot to fork their crypto there, because at some point we're going to go after it.
Yeah, what do you think about that? Because if you fork it, how do you approach? I mean, if you end up having two chains, that's an issue. And migrating is shutting it off probably for quite a bit of time. So forking it, is that straightforward? Even if you have
I have no idea. And I'm really not looking forward to the day where we have the capacity to harm Bitcoin, because I love my 10 fingers and I'd love to keep them. So yeah.
Yeah, because as that grows, that's the digital asset that is, in like 3, 4, 5 years ago, it might be equivalent to the gold standards, and that we're looking at 10 trillion or whatever. And then you come across and say, well, we need to fork it, but we have an issue. We have a lot of wallets, inclusive the founder, Satoshi wallets. We cannot just move them on, and we end up having to change, and that will change, and that will obviously not be possible. I think there are probably technical solutions to it, but
joke aside, there are algorithms that for now seems to be quantum resistant. The challenge there is in cryptanalysis or in cryptography is that you never have a proof of non-existence of an attack. The only security comes from the fact that many people tried and no one succeeded at breaking your code. And the challenge quantum is bringing is the short timelines, because there is a handful of promising post-quantum cryptography algorithms, but they haven't. I mean, they're fresh out of the box at that point. So it's gonna take time for them to become more quantum proof in some sense.
We are looking at critical infrastructure that needs to be upgraded, whether it's a replace or an upgrade or a fork or whatever, within the next 5 years. And for some of these bigger, corporations and critical systems, that seems like a very short time.
Yeah, but at the same time, you have to put things in perspective, because what quantum is about is not about breaking codes. That's just a side effect. Just like, when you think about it, classical computers arrived in exactly the same fashion. I mean, you have to see the imitation game in some sense. Now, the promise is such a breakthrough on everything else. In chemistry, if the promise is that 10 years from now, 15 years from now, the way we're going to design drugs might be widely different from what we're doing today, and that is definitely worth the hassle of updating our cryptography. Plus, we have time. I mean, now people are aware quantum computers are coming. The NIST is working on their standard. Let's just get moving, because the overall sum for mankind is definitely positive.
No, that I'll get back to that before we wrap it up, because I want to have some takes on that positive scenario. I just want to quickly just get your thoughts on the global ecosystem. So we have a lot of traction with the big players. I mean, you have a significant funding round behind you. There are promising players in Europe that have similar valuations and have had bigger rounds, but still they seem, in comparison to some of these large, deeper pockets in the US, they still seem like peanuts. If you look at the big, 7 tech companies right now, if you look at the numbers of accessibility. And then we have China, which we don't have a lot of overview of what's going on. Do you think we, as I speak as a European with you, and I'm, admire what you do and would like to see these companies take a front row in the global race. Do you think we have substantial scale capital and speed in Europe to keep up with the global players?
Yeah, the answer is definitely yes. I'm an extremely firm believer in European tech. I think, but it's gonna take a lot of audacity in almost a military sense. It's about establishing that bridgehead and hoping that the cavalry will join. So maybe to elaborate a bit. So China have zero idea. It's very hard to understand what is where they actually stand. And for me, it does not really matter, in the sense that it's gonna be two sealed markets, completely shut off one from another for at least 15-20 years. Whatever happens in China, we know they're dead serious about it. We know they have great talents. I mean, it's but doesn't really matter. Now in the US, you have to remember that they're burning a lot of capital. At the same time, those Magnificent Seven, they are not focused on quantum. Their top leadership is not thinking all day about what is the next bold move they can do in quantum. They're all about AI. I mean, Mark Zuckerberg is not spending $1 billion on a quantum researcher. He's trying to spend it on an AI researcher, and that is really the opportunity each time at each technological breakthrough for startups to challenge incumbents. It's the fact that the top leadership of those incumbents have so much noise around. It's hard for them to understand what are the bold moves they should be doing in this peculiar field. Now, we have serious contenders even in the startup world, and the challenge is rather, as you mentioned, the access to growth capital. And here, I mean, the problem is perfectly understood. I mean, it's in the Draghi report, and it's all about consolidating our financial markets, make sure we're able to concentrate capital efficiently. But it's also about Europe being able to make decisive moves, and picking winners and losers in a proper and well-structured way. It's not about authoritarian approach of top-down picking the right player. But in the next 5 years, we need to establish two, maybe at most 3 main European players on which we bet on. And the only time in my short life I've seen Europe deliver at scale, with audacity, with unity, is during COVID. What Europe did during COVID was remarkable, but we had a clear crisis. The problem for quantum is that we're missing the clear crisis, and then you fall back in all the pitfalls of the European Union, which is is it fair between different geographies? This one is going to benefit more, and you're not thinking about the overall capacity. And at the same time, we're all so much suffering of the fact that there is no European tech scene as there is a US one. So we need to kickstart that ecosystem, and it's going to take a lot of audacity. And I think I'm not going to ask for politicians to make a miracle. It's for us, founders and entrepreneurs, to create that opportunity and establish that bridgehead, and then call the cavalry. So let us make them dance, as Satya from Microsoft would say. Let's make the US players dance a bit, and we'll see how we can move from there.
That's a beautiful statement, Théau. I like that, and I think that coming together amongst the players, you have in IQM in Finland, you have been good with Jan Goetz, you have good people and good players that are doing the various approaches. If they team up, come together, of course, at the end of the day, you might be pitching for the same capital, but you're just having that European value system and just driving that. I think that's very powerful, and I really admire what you're doing, and I think that's a great approach to have that essence, that you also take that audacity to push for that, and I think that's a very good thing. So yeah, but what you said that there are so many promising things, and I totally agree. There are so many things that you could cure diseases, you could tap into understanding of longevity even, or whatever. You could start to play with quantum AI and look at simulation of different foundation models for structures to build, minds instead of simulating brains, and all of these philosophical questions, tapping into the foundations of ancient old philosophical questions into our realm of consciousness, or, what is life? And all of these things are ahead of us. And as we have those, new computational superpowers, and we get into those new algorithms and we ask those new questions, aren't you worried for the future of humanity? Are you all net positive that this will be good? I mean, set aside the fact that these technologies can also be used for, bad purposes, for military or whatever. In a general note, if we just have progress to that speed that we are foreseeing in such a short timeline, do you think that is a all positive path for humanity?
I mean, the point you're making is really always the question of, does technology necessarily comes with instability? And yeah, obviously, I mean, the greater the power, the greater the responsibility, in some sense. And yet, I mean, the doomsday clock has never been that close to midnight, but it still hasn't. I mean, so far we had no nuclear war. I think there is some wisdom in mankind where it's not apparent when you read the news and every day, but at the end of the day, there are reasonable people everywhere. And so far, if you smoothen a bit the timeline, history has been a net positive. So you have bumps on the road, and the timeline. What I fear is rather that as we deglobalize, we create more technological competition between continents and part of the world, and that means that societies will be strongly incentivized to fight against technological monopolistic positions, so they need to invest in tech at all cost. And you're seeing that at some scales in AI, where at the moment, all the alignment research and even just copyright debate is no longer relevant. It's all about surviving the attrition war that is at play in that tech field. So the question for us as Europeans is, how can we still use the only lever we have to create wisdom, which is culture? It's through film, it's through stories, it's through how we digest technology as an ensemble of humans, is through culture. And so we're gonna need a lot more Netflix shows featuring what quantum could do, or whatever sci-fi means that could mean, because this is the role of culture and societies to help us be more wise together. My role is very different. My role is to provide the capacity. And then it's not my role to decide whether this should be legal or there should be some barrier to the usage. And I'm all for the lawmakers to have a hard look at it and carefully think about it. But we need to respect everyone's role in this ecosystem, because so far it has been doing not too bad. It's far from perfect, but it's not too far. And since the physics allow it, someone will build that machine. So I think Europe, it's a personal opinion, has been somewhat more reasonable than other parts of the world when it comes to technology and its role. And so we need to show the way. So let's do exactly that. I will build the machine. The culture should help us digest what it means for societies to have access to that kind of power, and lawmakers should control its access, and should they or not, or encourage it? I don't know. They should think about it for sure.
But let me play with that just a little bit, because I would like to pick your mind on how I approach this, and one of the things that I'm working on is built around the future of humanity, and I call it a tomorrow mensch. So what is going to remain of us when we move in that direction, and what I look at is, I agree with your journey looking at humanity and our story as a line of progress, with a lot of challenges, obviously not perfect by any means, but we're living in progress. And throughout history, when we understood that we were confronted with an existential threat, you mentioned nuclear, we didn't end humanity, right? And
so far,
the same goes for a lot of these things. But the challenge is then we had the possibility to do stupid stuff and error correct, right? And my worries are that when technologies become so complex and you build these machines that have some kind of, maybe even agency, but at least some kind of recursive learning or some kind of foundational models that, guide you some kind of super intelligence or some AGI scenario, and they are on these computers, they are too complex for us to comprehend. So the alignment problem, so basically if we have goals that we intentionally see as humanity as good, the complexity is that we don't, cannot anticipate the implications. So security and progress then becomes less about trial and error and more about what kind of future is worth striving for. I would like to take, how your thoughts on how this type of scenario is different now than in previous paradigms.
Yeah, I mean, I'm fairly aligned with how Yann Lequin from Meta thinks about AI, for example, and not how he thinks about quantum, but that's for different reason. In the sense that, first, I really do not believe in the singularity. I not only I think we're very far from that, but even when it will happen, I have a hard time believing it could be that kind of feeling. Because when you think about what's going on at the moment, is that for frontier model, we're already using global scale computing capacity. It's not as if all of a sudden the machine could unlock a billion X more compute in some sense. So it's already saturated. And I think as we move forward, what we're saying is that computing is becoming more and more of a fundamental economic resource as energy was in the last century. It's something that is consumed by businesses to create value. And so we're maxing out energy usage within the bounds, we will max out always the compute usage. And so it's very hard. For the same reason, you cannot have an energetical singularity. You won't have an energetic singularity, computing singularity in some sense. Plus, I mean, we need to be extremely humble. Our computing machines are really not that powerful when you compare to what nature does. In terms of energy efficiency, of how cheap it is. I mean, it's extremely cheap. You just need to have fun with another person, and you created a new computer, and 9 months later. But yeah, that's kind of how cheap it is to build. So I think I'm fairly optimistic that it won't happen all of a sudden. Will still be extremely relevant, and the way I would think about it is rather to focus on the structural incentives. What I'm more worried about is how the rules of the games, as in the global stage, what are the incentive of countries, of individuals, of corporations to behave in certain ways. Because those are, for statistical physicists, those local parameters of incentives can create some completely different global behaviors. And so I would be way more worried about aligning the incentives of individual corporations and government with what society seems to agree on, a greater good. I'm not sure we're able to define that, than to align the machine itself. Because I think this is just going to be a consequence of the first ones. The problem we're facing at the moment, for example, just limiting ourselves to AI and copyright infringement, is that there is absolutely no incentive for corporations to respect copyright laws at the moment in AI. And since they have zero incentive to do so, nothing good is going to happen in that direction. And so I'd rather engineer the rules of the game than the best play directly.
Right. There was an approach to that, with a very simple approach to add that insurance policies that would be really incentivized for having insurances in place, because then you would have like the structures of a classical insurance mechanism for the policies which is skyrocket if you would not obey. And I thought, I mean, it wasn't really practical, but there are maybe some ways to find regulations or balancing mechanisms. But I think, what I been looking at with my co-author is basically this challenge of, regardless of how, if there's a technological singularity or whatever you want to call AGI or SI or whatever that point might happen, I think still having that super intelligence solely externalized in a machine is at least a very challenging task to us as a species. And what we have been pondering is that, can we build an artificial human intelligence? Can we, coming back to hacking chemistry and biology, and starting with a human being, starting with a mensch, and enhancing that to be able to cope with the complexity. So you have, biological substrates, you have some nanobots, and you measure, and you start to rebuild the body and the whole essence. Because that is, if you look at the efficiency of nature, I am also very agnostic to our brain as a computer or having quantum phenomena. But, there is always nice to romanticize that there is something that is humane, that is different than the machine. And therefore, I think it's utmost important to keep it. So what we have been thinking about is to say, okay, how can we build an artificial human intelligence? And this is also why I, hope that you build all these machines, because obviously we'll need this computational understanding and tackle all these challenges. But what do you think about, the threats of AI in that context, when you say that there is not a singularity, but couldn't it be so that it is still so efficient and so powerful that it would be difficult for us to comprehend when, building these organizations without having the rules in place? Or do you think the rules will, fall into place because we will realize the threats and group together?
Yeah, I'd like to push back a bit on several things you just said.
Yes, please. Please do that.
Because one could argue this is history repeating itself all over again. When you think about it, when we build machines, mechanical machines for I don't know, iron smithing, whatever, you can start thinking about the machine, saying, "Well, I'm comfortable using a hammer. After all, it's my strength that matters. It's only helping my strength deliver impact." But all of a sudden, you're bringing that mechanized, I don't know, press, whatever, that seems to have infinite power built in it. When it comes to the level of strength it can apply, of force it can apply on the metal is nothing compared to what humans can do. And if it goes south, I cannot stop it. I cannot fight against it mechanically, because my strength, won't be able to compete at all with the machine. And that's absolutely true. If you go in any modern factory, you stand far from the machines, because they won't blink before crushing you into the process. And in my opinion, intelligence in the broad sense is no different. And we've been taming. We've been playing with levers as humans throughout history. That's the whole point of since the Stone Age, is to find clever ways to do things that we couldn't without tools or without help. When we tamed animals to farm, those are animals. If you parallel intelligence with strength and kind of, there is a lot of things in common. You're trying to align what the bull wants to, where he wants to go in the field, with what you want him to do, and you're trying to find things. But we managed to do so, and I'm pretty sure we will be able to digest that as society. There is nothing fundamentally different. At the end of the day, it's all about aligning incentives for everyone involved. Now, in terms of the essence of humans, I'm a strong believer. This is a very personal take, that we're nothing more than biological machines. And I'm not so sure there is that much thing quantum. I'd be extremely surprised if there is more. If there is any remote entanglement within the brain, given the level of noise of how classical the chemical reactions themselves very locally can have some quantum effects in them, but it's extremely local both in time and space. And then we're just big molecular machines, in my opinion. So this again will be extremely humbling. One could argue also, another aspect which might actually progress faster is witnessing extraterrestrial life, and just finding, I don't know, anything, a few amino acids or early building blocks of life far from Earth will be extremely humbling for everyone, and help us think about that in a broader way. But we'll have time to digest all that. Don't be worried.
Promising. No, but and then you're not so So looking at Penrose and Hameroff and microtubuli, you're seeing that those are probably just local phenomena that has nothing to do with a higher state of like a quantum computational power. Is that is that the essence of what you're saying? Probably. I think that's.
If there is anything quantum about consciousness, that will completely break my understanding of quantum mechanics, in the sense that it's so hard to escape decoherence, and biological living cells are so messy with so many moving parts and so much thermal noise in it. If there is anything quantum, it's extremely well hidden, and the level of error correction has to be marvelous. I'm really not sure it's necessary. I think. But
Isn't it then so that the argument holds that you are saying that the mechanism of the human being is not particularly different than what we could build by technology? So we could get into that essence of creating almost an entire human being, and you would have some kind of computational structure for consciousness. Because if that is true, that, paired with the reasoning and the infinite access to knowledge of a supercomputer or a humanoid robot that is interconnected to 100 million or 10 billion other entities that are applying these knowledge in real time, in reality, and have an infinite speed of learning as all of these are adapting these theories into real life. If there's, nothing magical beyond our, physical access or computational power with the human being, then it seems fair to have an argument that could lead to such a singularity moment or a humanoid robot that could, skyrocket into some kind of higher state of consciousness or just, have a super intelligence that could control us. Or is that not?
No, because I think the point I'd challenge is the infinite access to. It's completely constrained by the resources available. And when you think about it, those frontier models at the moment, they're absolutely not.
What are the resources that it's constrained to? I'm just trying to get your argument.
Every aspect of it, the energy, connectivity. The number of transistors is still much smaller than the number of synapses you have in your brain. So it's not that magical in terms of orders of magnitude. Even the speed of learning at the moment, AIs are really bad at learning compared to organisms, living organisms. We use global scale computing infrastructure for months, burning I don't know how many tens of megawatts continuously over months to just learn to speak and barely reason, and learn by heart most of the internet. Okay, it has a great memory. That I'd give it to you. It's really amazing in terms of memory.
But look at the timeline, for example. If you look at like a timeline, let's put a baseline on. Obviously, the pre-training structures were beyond a reasonable learning mechanism you can build on the substance of the past. So let's look at the GPT moment, and we fast forward now 3 years. So we are looking at a toddler that has start bearing to adapt to, a physical reality and learn. And I would argue that the reasoning in a latest update of Grok or GPT with agents is when you would find ways to do that in a more energy efficient way with pre-trained models and world models and other foundational structures, that the progress, if you take that into the future, you can build on that. And if you say you would have a born baby today and you would have 18 years to grow into a grown-up, where are we on that scale in 18 years from now? And I think that is, to me, I agree with your analogy that we are not at all there in the hallucination, the challenging, and obviously to apply it to physical reality is one of the biggest challenges, and we are running out of questions to train. But if we look at a newborn today and we would say, give it 18 years to grow up, where are we then? And that's what I'm looking at. There must be some restrictions or limitations, or some smart people sitting in Paris with an off button that could just turn it off eventually, which would be a good scenario. But I still am slightly surprised about the speed of progress. And I ponder a lot about, where are the limits and where is the control mechanism for this?
Yeah,
But you seem to have a much more positive view.
You must have, everyone at some point in their life meets someone that is much smarter than them. For example, at our corporate retreat a few weeks ago, we had Cédric Villani, a famous mathematician, and so I had dinner with Cédric, and the guy is a Fields Medal. He's the way he looks at mathematics is just way beyond my understanding. He's seeing patterns in things where I see nothing, and yet I was having dinner with the guys living in the same world, and at the end of the day, we feel the same kind of existential question about why are we here? Why is there something instead of nothing? And Another way to say that the AI can get as smart as they want. They won't solve the question of why. Why is there anything? And so, what should they do? If because the question of the threat say implies that they have an incentive to do harm, or they have an incentive to go somewhere, but there is no incentive other than just for us it's hardwired. It's a survival instinct. It's something nature has hardwired very deep in our brain, and the reflexes you have is absolutely subconscious. I mean, it's you avoid a bullet, whatever, you try to survive, but it's hardwired deep. And so intelligence by itself has no because there is no greater obvious meaning or absolute scale of intelligence. However, it won't have any built-in epiphany moment where it says, I must do that. It will only follow the incentives we built in, just like nature has for survival purposes built in the survival instinct in ourselves, and all we do is try to pass on life and escape thermodynamic equilibrium. But this is why it remains a tool until it has built-in alignment and purpose and things like that, which is hardwired. I mean, I have two daughters, and it's fascinating for me to watch them grow and see how much either the system is awfully chaotic in how they learn, or how much things are native, I mean, built in within the kid, in their personality, the way they approach. They have two completely different personalities, and yeah, we might have done things slightly different from, but yeah, it's really hardwired. There is a lot of things hardwired. So I think for tomorrow's machine, we learn to appreciate our own making in their intelligence, how we built the incentives. And as soon as we learn that, the threat disappears. It becomes only managing humans and making sure, it's making sure no malicious human builds a malicious AI. Not that AI per se, by itself, by nature, could be malicious.
Théau, that's a beautiful way to wrap that up, I think. This is something that I'm looking forward to 2030, to have a glass of Chardonnay and sit down with you in Paris and look at Alice and Bob and how you have become a big player in this field. And we could look back at our assumptions today. And I'm sure we'll have some surprises. And thank you so much for spending the time and doing this. I picked up and learned a lot. And again, thank you so much for this wonderful conversation.
Thanks a lot, Anders.